Hello guys, this is Code and Code, and this is video editorial for the problem redundant connections second. It also has part one, and this is part two, right? And this one is of difficulty level hard, right? So let's see what the problem statement says, how you can solve this problem and implement the solution. All right, so let's get started. So, if you have solved part one of this problem, that's great. If not, you can go ahead and check it out. It's actually a harder version of the same problem, right? I've already uploaded the editorial for that. You can check that out also, right? So let's have a look at the problem statement. So the problem statement is simple. You are given n nodes, and you are given n nodes, and of course, it's a tree, right? It's stated in the problem statement. This is a tree, and you are given n nodes with n edges. Now, since it was a tree and you have added an extra edge into that tree, that's why it has exactly n edges, right? So we have n nodes and n edges, right? It was a tree, we have added an extra edge. Now, because we have added that extra edge, it's not a tree anymore. So the problem statement is that you have to find any edge that you can remove so that it becomes a tree again, right? And if there are multiple edges that you can remove, you have to return the one which appears last in the input, right? That is the problem statement. For example, and this time this is a directed tree, right? In the earlier version it was undirected tree, right? This is a directed tree. So the edge 1 2 means there is an edge from node 1 to node 2, right? 1 2 2, right? It's not bidirected. This is a directed tree or graph, whatever you would like to call it. So this is the problem statement. Let's understand it with an example. So let's say the input was 1 2 2 3 3 4 4 1 and 1 5. So 5 node, 5 edges. These are the nodes and edges. As you can see, this is not a tree anymore. So we have to find one edge and we have to remove that so that it becomes a tree again, right? So now, so since it was a tree and we have added an extra edge, so it kind of adds a cycle, right? Like this. Since this is a directed graph, it may or may not be a cycle, right? In this case, it is. But if 1 4 was added, it would look like a cycle, but it won't be a cycle, right? Now, so if you look at it, so this whole cycle, you can remove out of this whole cycle, you can remove any edge, and it will become a tree again, right? So if you take a look at this, in this example, I'm trying to explain that we can remove edge 4 1 and it would become a tree again, or we can remove 1 2, same story, 2 3, same story, and same goes for 3 4. All right, I couldn't just add extra graphics here because it took all the space. So 3 4 is also a candidate. So 1 2 3 4, we have four candidate edges, out of which we can remove anyone and it would become a tree again. Now, the thing is that which edge we should remove. So we have to, if there are multiple candidates, we have to remove the one which appears at last in the input edge, right? So if you see 4 1 appears in the end, right? This is the last edge of the candidate. So we will remove 4 1. And now we will have a tree, right? So the answer of this input would be 4 1. Right, so this is the problem statement. You are given a directed tree, we have added an extra edge, that's why we have n nodes and n edges. Because of that extra edge, we would have something like this. We would have kind of a cycle, right? Since this is a directed graph, it may or may not be a cycle. It would look like a cycle, may not be a cycle, right? So we have to find that and remove one edge, and that would make it back a tree. That's the problem statement, right? So now let's make some observation. So which edge to choose when we have multiple candidates, right? We can simply we may think that we can simply pick the one which appears at the end and remove it, but that is not the case. This one, if you compare it with part one, becomes a little complex. So one of the observation here is that since we are adding an extra edge, right, and this is a directed tree or directed graph, whatever you'd like to call it, so there can be a node with two parents, right? There may be a node or may not be a node. That means there may be 0 or 1 nodes with two parents, but not more than that. That means there can't be two or more nodes with two parents. If it is, it won't be turning back to a tree. after removing exactly one edge, because that's exactly what we have to do. We have to remove one edge and it would become back a tree, right? It won't happen. Let's say in this example we have two nodes with two parents, right? Two has 1 3 as parent, one has 5 4 as parent. Since we can remove only one edge, if I remove any of these four edges, 2 3 1 2, 4 1 5 1, if I remove any of these one edges, because these four edges are creating a node with two parents. In a tree there is no node with two parents, right? So these two nodes are creating issue. If I want to make this a proper tree, I should have zero nodes with two parents, right? So out of these four, if I remove any of the edge, it won't turn back to a tree. That's why in the input that is given to us, there can be zero or one nodes with two parents, not more than that. There won't be two or more than two nodes with two parents, right? This is observation one, and let's take a look at other observation. So here, so according to the problem statement, since this was a tree and we have added one edge extra, there are only three possibilities that the graph would look like. Either it would have a cycle like this, okay, this is a proper cycle, or it would have a node with two parent. For example, this, as you can see, this looks like a cycle, but it is not a cycle, right? Now, here we have a node with two parent, right? Either we will get a cycle, or we'll get a node with two parent, or we'll get a cycle and a node with two parent. These are the only three possibilities, right? So yeah, these are the only three possibilities. More than this is not possible, as we have discussed in the previous observation. There can't be a node, there can't be more than one node which has two degrees, right? And hence we won't have any more combination. Either we will have a cycle or not a cycle. We'll have a node with two parent or not a node with two parents. So if you look at it, it would create three different combination, right? And those three combinations are these. So we only have to deal with these three combinations, right? And then we can find the solution of these three different uh, configurations, right? So let's have a look at how we are going to solve each different scenario. All right, so let's talk about the configuration when we have a cycle with no node with two parents, right? So this is a proper cycle with no nodes with two parents, right? In this situation, no node with two parents, hence any edge you can remove from the cycle. So it would make a perfect cycle and there won't be any node with two parents, right? So it would have a perfect cycle. If it was not a perfect cycle, that means you can reverse any of these edges. In that case, you will have a node with two parent, right? So if we don't have a node with two parent, we will have a perfect cycle. If you get a perfect cycle, you can remove any edge. It won't create any issue. I can remove this, it will turn back to a tree. I can remove this or this or this, it would turn back to a tree. So when you have a proper cycle, you can remove any edge, right? Any of the candidate edge. So among the candidate edges, you can remove any of the edge, right? It won't create any issue, and hence we can remove the one which appears last in the input, right? Remove the edge that was added at the end in the input, right? It is specified in the problem statement. If you can remove multiple edges, all right. So remove the one which appears at the end in the input, right? So among all of the candidates, remove the one which appears at the end, at last in the problem statement. As simple as that for this scenario. For example, let's say if I have five nodes and five edges are given, and I'm going through the edges one by one. This is exactly like this the part one problem, right? Part one of this problem is kind of like this. We'll use DSU, right? So first of all, I'll process edge, first edge, that is 1 2. Are 1 or 2 connected? No, they are not connected. So I'll call DSU union operation to merge 1 and 2. Then the next edge, 2 3, not connected. So connect 2 3, 3 4, not connected. Connect 3 4. 4 1, 4 and 1 are already connected. That means this edge is going to add a cycle, and hence this is going to be your answer. We have discussed this solution in detail in part 1, right? So I'm not going into the detail of this. So basically you can process the edges from left to right, whichever edge appears at the end and creating a cycle. That is your answer, where you have a cycle when basically you don't have a node with two parent, right? Now, what about those two situations? Our result will be edge for one, right? Now, what about the situation when you have two parents and a cycle and a two parent, right? In this case, we have a cycle and two parents. In this case, we don't have a cycle, but we have node with two parents, right? So in case you have a proper cycle and a node with two parents, that can only happen if there is an edge that comes out of that cycle, right? This edge, which is creating a node with two parent, comes out of the cycle. It is not part of the cycle, right? So this edge you can't remove. If you remove this, you will have a node which is disconnected from other nodes, and hence you won't have a tree. If you have a tree, all of the nodes will be connected, right? So this node can't be removed. So basically, in the second and third configuration, which can happen in this problem, yeah, there appears a scenario where you will have a node with two parents, and not both of those edges you can actually remove, right? So we have two candidate edges that we can remove. For example, this node has two parents, 3 and 1. We have to remove one of it because in a tree there is no node with two edges, right? So sorry, there is no node with two parents, so we have to remove one edge so that it only has one parent, right? So these two edges will be our candidate. Either I can remove 1 4, or I can remove 3 4, so that node 4 has only one parent, right? Same in this case, 1 has two parents, 4 and 5. So these two edges, 4 1 or 5 1, are my candidates which I want to remove. But the issue here is that in the first case, where we have two nodes, a node with two parents, but it doesn't have a cycle, we can remove both of the edges. It won't create any issue. I can remove 1 4, no issues at all. I can remove 3 4, no issues at all. But in this case, where we have a node with two parents and also a proper cycle like this, that means a node is connecting from outside the cycle. So if you remove one of those edges, it would create an issue. For example, if you remove 5 1, now there is a cycle and you have disconnected a node. So in this case, you actually can't remove both of the edges. Even though we have two edges as candidate, one of which we can't remove. So how to deal with this situation when we have a node with two parent, right? We can't simply take two edges and remove the one which appeared last in the input. We can't do that because in this it won't create an issue, but in this, yes. If 5 1 was added after 4 1, it would become you would want to remove 5 1, but if you do that, the graph will be disconnected. It won't even be a tree, right? So let's see how we'll solve this problem, right? So the solution is simple. First of all, find out which node has two parents, right? If first of all, just go through the edge list, find the node which has two edges, right? Two parents basically. So if it has two parents, right, just save both of those edges. For example, in first example, 1 3 and 1 4 and 3 4, 1 4 and 3 4, I have saved as A and B. In the second example, 4 1 and 5 1, right? 4 1 and 5 1, I have taken as two edges of the node which has two parents, right? So those edges you have to save because you have to delete one of those edges, and that would be your result, right? So just save both of these. It is very easy. I'll explain using the implementation. Don't worry about it. And here I have explicitly told that the A was added before B, right? So edge B is added later. So we'll save edges A and B in such a way that A was added earlier and B was added later. So we know which one was added before and after, right? So once you have both of those edges, right, if you don't have any node with two parents, you can go ahead with the just finding the cycle, whichever edge appears at the end, remove that, right? That would be the first configuration. In second and third, it becomes complicated. You have a node with two parents, just save both of those edges, right? I'm taking two different examples to explain you both of those situations. So just save both of those edges, which are your candidates now. Now you have to see whether you can remove B or not, because there are scenarios where you remove B, which was added later, right? We have to remove the node edge which was added later, right? Out of all of the candidates. So we have to see whether we can remove B or not, right? So we have to make sure that we can absolutely remove edge B without making any issue. If removing B creates an issue, don't remove B, remove A, right? Because we only have two candidates in these two scenarios, either edge A or B. I'll try to remove B because B was added later. That is what problem statement says. If I can remove edge B without creating any issue, like in this example, B is my answer. Otherwise, A will be my answer. Because if I try to remove B here, right? the graph will become disconnected. It won't even be a tree, right? So we have to make sure, absolutely make sure that we can remove B. If we can't make sure that, we'll remove A in that case, right? So how to take care of that? So the way we'll do it is this, right? We want to make sure whether we can remove B or not. So what we'll do, we'll try to do the exact same thing. We'll try to see if any of the edge creates a cycle, right? And we'll do that without using edge B. While we are processing all of the edges, right, we know which edge is A, which edge is B. When we are processing, to check whether there is a cycle or not, right? If there is a cycle, we process to find out whether we have a cycle or not without using edge B, right? For example, B is added later. So in such scenarios, like in this example, where B would be this, right? The edge which was added later would be the one which, when you remove, creates an issue. So in such scenarios, we will not use B. So what we are going to do, we'll process the edge list without using B, right? One by one. So how this goes is this. So let's say in the first example, I'm going through the edge list. I'm processing 1 2, are 1 or 2 connected? No, so I'll make union. 2 3 not connected, union. 1 4 not connected, union. 3 4 edge 3 4 I won't process because edge 3 4 is B, right? I'm taking example of this graph only. This we'll talk about in a moment, right? We are talking about this graph only. So 3 4 is actually edge B, right? So I won't process this, right? 1 4 and 3 4, 1 4 and 3 4, as you can see, are edges which are creating a node with two parent. So 1 4 and 2 4 are our candidate. 1 4 was added before 3 4. That's why A is 1 4, B is 3 4. Now, as I said, while we are processing the edge list, uh, we won't process edge B. So I am at edge B. I'll ignore it. I'll go to the next edge, which is 1 5. I'll connect 1 5. 1 and 5 were not connected, so I'll connect it. So I have gone through the edge list, and without using B, of course, and I did not find any cycle. What does that tell you? It tells you the edge that you have just left out, that is the edge that actually creates a cycle, right? That means you can remove that edge and it won't have any cycle in it. That means you can safely remove edge B. So in this case, B will be your result. Yeah, you can remove B, that is 3 4, and that would be your answer. So what we did, we are going through the edge list again, one by one, without using edge B, right? And we'll see if after going through all of the edges, we get a cycle or not. In this case, we did not get any cycle. That means edge B, when added, will create a cycle, right? And hence B is your solution, and you can remove this, my bad. And you can remove this, right? So this is uh, this example. Now for the next one, where B will actually create an issue, let's go through that also. So in this scenario, this is the edge list: 1 2 2 3 4 1 5 1 and 3 4. A is 4 1, B is 5 1, right? 4 1 and 5 1 are creating a node with two edges, sorry, two parents, and 4 1 appears before 5 1. As you can see, that's why 4 1 is A, 5 1 is B, right? Now again, we'll process the edge list without using B, right? So I'll process 1 2, are 1 or 2 connected? No, they are not connected, right? 2 3, they are not connected. 4 1, they are not connected. 5 1, 5 1 is B, I will ignore it, right? And then 3 4. Yes, 3 and 4 is actually creating a cycle. See, after going through the edge list, there are only two scenarios. Either after going through all of the edges, it will create a cycle, or it will not create a cycle. In previous example, it was not creating a cycle. And which edge we did not use? Edge B. That is why B was your answer. If B had been added to the graph, it would have created a cycle, and hence B is your answer, right? In this case, we have not used B and we are still getting a cycle. What does that mean? That means B is not part of the cycle. That means if you remove B, right, it would disconnect the graph, and hence B cannot be your answer. In such scenarios, A will be your answer, right? So in here, you will remove A, which is 4 1. 3 4, so yeah, 3 4 is creating an issue, and we have already gone through edge A, right? Only candidates are A and B. If you can't remove B, you have to remove A, right? You say, yeah, but the last edge which is creating an issue is 3 4. Yeah, but that is not the edge which is creating a node with two parents. We have to take care of that also. I can remove 3, 4. It won't have any cycle anymore, but we will still have a node with two edges, two parents. In a tree, you can't have that, right? That's why if there is a node which has two parents, you'll find both of those edges and you will remove one of those, right? Even though in a cycle there can be multiple edges which you can remove and the cycle is gone, but you have taken care of the cycle, you have not taken care of a node which has two parents. That is why when you are going to remove an edge, it would be one of these two, A or B, right? So if I summarize it, would be something like this. You are going through the edge list. First, you have to find out if there is a node with two parents, right? So you are going through the edge list, right? If you did not find any node with two parents, right? It creates the first configuration where you have a cycle only. If you have a cycle only, you can remove any edge, right? So you will remove the edge which was added at the end, right? If you have a node with two parents, go through, just save them, those both of those edges which are creating a node with two parents, right? In this case 1434, in this case 4151. Save those, right? Go through the edge list again, using the union find, and check whether without using hb, is there any cycle in it. If there is no cycle, b is your solution. If there is a cycle, a is your solution. As simple as that. If I take you to the solution, here it is, as simple as this. Let me just increase the font size. Come on. Yeah. So you see, simple find operation of union find, right? I'm using path compression, as you can see here, right? Now, what I'm doing here, we have given an edge list. Size of edge list will be n. That is the number of nodes. Same the number of edges, right? So size of edges will tell you the number of nodes. So I'm getting the number of nodes, creating a parent array that will be used in finding out which node has two parent, and also it will help you in DSU, right? You need a parent array, right? So for n plus 1 nodes, I'm initializing the parent as 0 because nodes are numbered from 1 to n. None of the nodes can have parent 0, right? So 0 will tell you invalid parent. Then I have candidate A, candidate B, basically A and B edges, right? So I'm going through the edge list, right? One by one. So uh, for each edge, E0, E1 represents there is an edge from E0 to E1. E0 is parent and E1 is child. So there is an edge from parent to child. Here I'm checking whether this node child already has a parent. So if parent of C is not equal to 0, if parent of C is not equal to 0, that means C already has a parent. That means we have found a node with two parent. So which is parent of C and C. This is one edge, right? There is an edge from parent of C to C. So this is one edge, parent of C to C. Another edge is the one that we just found, that is E, right? So these are two edges. My bad. My cat is creating some issue. Let me just mute this. Come on. Uh, Sorry. Yeah. So these are two edges. One of the earliest found edge was parent of C to C, right? And the latest found one is E itself. So candidate B is E and candidate A is this one, right? If parent of C is 0, that means it doesn't have a parent. So we'll update its parent. As simple as that. Once you have gone through the whole edge list, you either have candidate A and B, in case there is existing node which has two parents, or they will be empty in case there's none of the nodes. There are no nodes which have two parents, right? So this is step one. After that, what we'll do, we'll use DSU. So I'll update this parent array. So in DSU, what I'm using, parent of A is equals to A in case A is the parent, right, of the DSU. That's why for each node I'm updating parent of I is equals to I, basic DSU stuff, right? After that, I'm going through the edge list again, making sure that I'm not using edge B. You see, if current edge is B, continue. So I'm not using edge B, right? Now I'm going through the edges and I'm checking whether E0 and E1 are, basically I'm applying the find operation, and I'm checking whether they are already connected or not. Basically the nodes which current edge is trying to connect. If current edge is trying to connect two nodes which are already connected, that means their parent will be same. A and B will be same. If this edge is trying to connect two nodes which are already connected, that means we have found a cycle. If we have found a cycle, what we are going to check? We are going to check whether there exists a node with two parents or not, right? So that's exactly what I'm checking here. So if candidate A dot size is greater than 0, that means candidate A is not empty. That means A and B, two edges are there which are not empty. That means we have a node with two parents, right? So if we have a node with two parents and we have found a cycle without using B, what does that mean? That means that without using B, we already have a cycle. So this case, right? Without using B, we have found a cycle. So what will be your solution? Your solution will be edge A. So you'll return edge A. Otherwise, if there was no node with two parents, but we still found an edge that creates a cycle, what does that tell you? It tells you we are at configuration one. That means we don't have any node with two parents and we have found a cycle. That means the current edge that is creating a cycle is the latest edge that creates a cycle, and hence you can return that. So this is that case, right? Current edge is creating a cycle. You can return that. This is configuration one. Otherwise, if they are not connected, right? If they are not connected, so what we are going to do? We are simply going to update the parent. Basically, this is union operation, right? If after going through the whole edge list, I did not find any cycle, what does that mean? If I'm going through the whole edge list and I did not find any cycle, what is this? This situation, configuration second, in which you have a node, you have a node without a proper cycle, right? So you have gone through the whole adjacency list without using edge B and you did not find any cycle, right? So you have gone through the whole adjacency list, edge list, my bad, not adjacency list. You have gone through the whole edge list, right? You did not find any cycle. That means without using B. That means if you had used B, it would have created a cycle. That's why B is your solution. That's why from here we are returning B. As simple as that. All right. So yeah, this is how you solve redundant connection 2, which is a hard problem. The easier version of it, redundant connection 1, we have already solved. I have already uploaded an tutorial for that also. Yeah, so yeah, this is how you solve redundant connection 2 using DSU. Right. So this is it for this lecture. Thank you guys for watching. Until the next video drops, keep coding. Thank you.